The universe is filled with exotic objects, strange objects once described only by mathematical models, their existence limited to theoreticians' equations, journals, and science fiction novels. Only with thorough research, and in some cases a little luck, have these objects been revealed to us. The 1930s, the golden age of physics. Albert Einstein had changed our perspective of space and time 20 years earlier, and his revolutionary theories were beginning to prove themselves. In 1932, Sir James Chadwick, working in a laboratory, discovered the neutron, a neutrally charged subatomic particle. The same year, Russian physicist Lev Landau predicted that neutron stars might exist if neutrons could resist the immense pressure and be able to support the crushing mass of a star. Astronomers and astrophysicists soon theorized that a neutron star could be formed by the collapse of massive stars in explosions called supernovae, leaving a dense, city-sized sphere of tightly packed neutrons. Several years later, Robert Oppenheimer and his colleagues mathematically modeled the neutron star. Mathematics play a vital role in astronomy. Physicists and theoreticians use their calculations to predict conditions in the universe. The blackboard prediction of a neutron star was one that astronomers never thought they'd be able to observe.
Neutron stars were first postulated by Oppenheimer, actually. They were thinking about what happens when stars run out of fuel and collapse. Chandrasekhar had earlier shown that you have to get a white dwarf from a normal type star's collapse, and he showed that a white dwarf couldn't have more than about 1.5 solar masses, or it would shrink to nothing. And Oppenheimer said, well, I wonder what happens then. And they figured out that neutrons would be another place where the collapse could be halted by essentially the same thing that electrons do for white dwarfs, neutrons could do for somewhat more massive stars.
We are familiar with the idea that like charges repel, such as two electrons repelling one another. In a similar way, if too many particles with any similar characteristics are squeezed too tightly together, they will also resist that squeezing. This principle applies to neutrons as well as electrons. Oppenheimer's mathematical model for how a neutron star could form starts with a high-mass star exhausting its nuclear fuel, going supernova, and collapsing into a 10-kilometer ball with nearly 3 times the mass of the Sun. A neutron star is an object so dense that a teaspoon of its compressed material would weigh 1 billion tons. As the star shrinks to its final compact size, its rotation would increase proportionately until it spins some 100 times per second. Its initial surface temperature would exceed that of the Sun's core and would take an incredibly long time to cool down due to its small surface area. It would also possess an equally powerful magnetic field, trillions of times stronger than the magnetic field of the Earth. The model described an object that astronomers of the early 20th century never expected to observe with the best telescopes of the day, an object only for discussion at conferences and in classrooms.
So they computed in the 30s that you could have these things, but nobody actually expected to find them or be able to see them or anything. And so they were discovered very serendipitously by radio astronomers.
By Jocelyn Bell Burnell in the UK. And she was a PhD student at that time, and she was working actually on a project involving quasars. They had a new radio telescope there that she was using, and she was doing a lot of the engineering and setup herself. And so she pointed at a particular object one time and found that she was receiving a very strong but intermittent signal. And so it was this sort of blip, 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 and it was very regular. And that does not seem astronomical. We don't expect things in nature to be that regular. And so she assumed, as I think anyone would, that it was an instrumental problem. And so they spent days, she and her advisor, trying to track down what could possibly be causing this. When it wasn't instrumental, their next thought was that it must be artificially generated, but somewhere off the Earth.
And everybody then had a great time looking at what they called, at first, LGMs, little green men. Must be somebody's engineering. And then, when they found a few more in the sky, they began to think, well, that's a lot of extraterrestrial intelligence out there. I mean, if they're just all over the place. And indeed, the whole theory of neutron stars had been developed and published probably 30 years earlier, and everyone had kind of forgotten it. But when Tommy Gold heard about this, he said, I know what that is.
What Gold, a British astrophysicist, knew was that the predicted neutron star would have particular characteristics, the same ones Jocelyn Bell had observed.
Electrons in the atmosphere of this neutron star have a lot of energy, and they can rotate around the magnetic field lines and lose some of that energy. Think about a lighthouse, right? The light's shining all the time, but you don't see it except when the mirror that's focusing that light comes across your line of sight and then rotates away. Just like with a neutron star, with its magnetic field, occasionally that beam of radiation will come at you and then it will rotate away. And that was the radio pulses that Jocelyn Bell was seeing. And the neutron star, in this case, was spinning once every few seconds. Neutron stars, in fact, can spin as fast as 1,000 times a second. And this astronomical phenomena was, in fact, in part, theoretically predicted much, much earlier. And Tommy Gold put together that prediction about this dense neutron star with the radio pulse production mechanism and said, that's what your pulsars are. These absolutely regular pulses that you're getting are due to a very rapidly rotating object, a neutron star with a magnetic field. So we learned something new about the universe.
Eventually, astronomers replaced the name LGM with the term pulsar to describe a source of short, precisely timed radio bursts coming from a rapidly spinning neutron star. What Oppenheimer predicted, Jocelyn Bell observed, and Tommy Gold linked together is the relationship of neutron stars and pulsars. Their fantastic rate of spin, coupled with their equally fantastic magnetic fields, turns young neutron stars into cosmic lighthouses, sweeping their beams of light out into space. If they intersect the Earth, we see them pulsing as the neutron star spins. Since Jocelyn Bell's discovery, thousands of pulsars have been identified. Today, astronomers study neutron stars at many different wavelengths of light: radio, infrared, visible, X-ray, and even gamma ray. Astronomers can obtain measurements of neutron stars indirectly when they exist in binary systems. By studying the motion of the neutron star and/or its binary companion, astronomers can refine their models of these compact objects.
So whenever one has a system consisting of two masses, whether it's two stars or a star or a planet, both of them will move around the common center of gravity. The closer the two objects get to each other and the more massive they are, the faster is the orbital motion. We see this in the solar system. Mercury, for instance, goes around the sun faster than the Earth, and the Earth is faster than Jupiter, and so on. If you make the star more massive, the motion also gets faster.
A neutron star in a binary system also dances to this gravitational tune, and from that, its mass can be determined. Observations of binary systems confirm the mathematical models that neutron stars have a maximum limit of about 3 solar masses, about twice that of a white dwarf. But in their observations of binary systems, astronomers have detected even denser objects. In 1939, Oppenheimer collaborated with several other scientists and eventually submitted a paper on how even denser objects could form. Using quantum mechanics and Einstein's theory of relativity, they refined the calculations of an earlier astronomer who postulated an object whose gravity was so strong that even light could not escape from it. The object, later known as the black hole, would not be indirectly observed until the 1970s. A black hole, also known as a singularity, is a massive object that has collapsed all the way down to a mathematical point, an object with zero radius. The math states that density and gravity become infinite at the center. If even a beam of light gets too close to a black hole, it cannot escape.
To understand a black hole, you really have to understand Einstein's idea about gravity as the curvature of space-time. And the real way to understand a black hole is that it's an object in which space-time is curved so much that it's closed around on itself. So light, even light, thinks it's traveling in straight lines, but straight lines around a black hole are closed curves within it. So the light simply can't get out because it doesn't know a way. There is no path through space-time that leads out of a black hole. Space-time's all wrapped up inside.
Astronomer Carl Schwarzschild was the first to model a black hole using Einstein's relativity. He calculated the critical distance one must be from a black hole such that its gravity becomes so strong that neither matter nor light nor any kind of information can escape into the rest of the universe. We now call this distance the Schwarzschild radius. Because light cannot escape from inside the Schwarzschild radius, no information from inside can get out. The edge of this sphere is therefore known as the event horizon, because any events which happen inside it are beyond the horizon for us outside. Once an object falls in and crosses this event horizon, it is lost forever.
Black holes aren't huge vacuum cleaners that are going to suck up everything in the universe. Black holes are just strong gravitational fields. And if you took a black hole the same mass as the sun, and you quickly plunked it into the middle of the solar system instead of the sun, the orbits of the planets wouldn't change. We would be far enough from that black hole, we wouldn't feel any of its effects except the same amount of gravity that the sun had exerted, and the Earth would continue along its orbit around the black hole. Of course, we wouldn't get any sunshine, but the gravity wouldn't change, and the orbits of the planets wouldn't change.
What makes black holes really interesting are the events that would take place if someone or something crossed the event horizon. If you're too close to a black hole, you're gone forever. But just a hair above the event horizon, things get pretty interesting.
If you fall towards a black hole, your experience is very different from people who are watching you fall from a safe distance. So what you see is you approach the black hole. Of course, you speed up, and in fact, you end up going more or less the speed of light just before you hit it. The black hole looms in front of you very quickly, and it bends light around it. So the universe actually you begin to see images of the universe from further and further away. So it's kind of like a ring of light with a dark center that grows in front of you, and then the blackness kind of overtakes you. Other bad things happen too, of course. You experience tremendous tidal forces. Your feet have a lot stronger gravity on them than your head, and so it actually pulls you out into a string of atoms before you get there. And it's all over very quickly for you. This happens the last part happens in a few milliseconds. Meanwhile, though, your buddies on the outside see something very different. As you drop towards the black hole, you begin to look dimmer and dimmer as the light that's leaving you has to climb out of this gravitational well further and further. It looks dimmer, and it gets redder and redder.
This reddening of the light, or lengthening of the wavelength, is known as gravitational red shift, caused by the loss of energy that light experiences as it tries to overcome the gravitational pull of the black hole. The trip continues.
But even more strangely, time itself appears to slow down. And Einstein has shown that this happens generally in gravitational fields, but of course it happens in spades near a black hole. So in fact, what happens is it looks as though you never fall into the black hole. Time slows and slows and slows and essentially comes to a halt at the edge of the black hole. So you look like you're frozen there, about to fall in for all eternity, except they can't really see you because no light is really getting back to them.
To an outside observer, it takes you literally forever to fall in. To you, however, your time appears to flow normally, though not for long. Once you enter the event horizon, things end rather abruptly. This slowing at the edge of a black hole is called time dilation, the slowing of time caused by an immense gravitational field. This leaves us with a seeming paradox. How do astronomers detect black holes if no light or information can escape them?
Well, the role that the black hole has played in the development or the evolution of astronomy is very interesting. It started out as just a mathematical concept, as an idea where what happens when gravity becomes too strong and nothing can get away from it. And it was thought that this was just basically a mathematical problem, a fictional problem. But as more and more study was devoted to astronomy, to the sky, we found areas where large amounts of mass could be seen moving objects around. The mass itself couldn't be seen, but large things were found moving around in apparently empty space.
Astronomers search for black holes in different ways. For instance, they can be observed indirectly in a binary system by watching for their effect on the motion of a partner star.
And by analyzing that motion, we can determine the mass of the central object. If that mass is not very high, say up to roughly 3 solar masses, it could be something like a neutron star. But if it's more massive than 3 solar masses and dark, then it is very likely that it is a black hole. So the evidence that we have for the existence of black holes is somewhat indirect from this kind of mass measurements that are derived from the orbits of binaries. But we think that the existence of a black hole is still the best explanation for this kind of motion.
The direct method of observing a black hole deals with its binary companion star and the rather tempestuous relationship between the two objects. Sometimes these binary companions can dump matter into the black hole. The matter piles up just outside the event horizon, forming a disk. The matter gets incredibly hot and glows very brightly across the electromagnetic spectrum. Ironically, this means that black holes can produce some of the brightest objects in the universe.
Stellar mass black holes, those that have a range of masses typical of massive stars like 5 or 7 or 10 solar masses, are found when they steal material from a companion star that's gravitationally bound to the black hole, and the black hole eventually steals material from this companion star.
You would see a disk possibly, or a big donut possibly, of just gas swirling around this black hole at the center. And it's in orbit. It's not being sucked in like a vacuum cleaner would suck in dirt. It's in orbit. So we call that an accretion disk. Now on the inner edge of that disk, probably, undoubtedly, material is breaking off, getting caught in the gravitational field so that it will eventually spiral into the black hole.
And the rate at which it swallows the material can change with time, and so these things flicker, especially at X-ray energies. And so the Chandra and other X-ray observatories can find these flickering or even bursting X-ray sources.
The infalling material from the companion star sometimes creates jets of energy that can be observed in the radio portion of the spectrum.
Jets. Now, nobody really knows what's happening, but often, not always, you'll see these enormous jets that emit radio waves. Nobody really knows what makes the jets stay so collimated. In other words, the beam stays like a pencil beam. That's what we mean by collimated. For many, many light years, this beam stays very collimated. We don't know what makes it do that. We think it's magnetic fields, somehow, constraining gas to stay along magnetic field lines. But we don't know for sure what causes those field lines to be so tightly woven, so tightly wound, and for gas to be accelerated so rapidly along those magnetic field lines, stay together. Electrons spiral along the magnetic field lines, emit radio waves for such a long distance. Nobody really understands the mechanics of what makes that happen. It's an area of research that maybe the next generation of astronomers is going to uncover. It's an area of active research now, but we still don't know.
So how do the massive compact objects form?
Most massive stars that collapse produce neutron stars in their core, and that halts the collapse there. But just as with white dwarfs, there's a limit to how much mass a neutron star can have and still hold itself up. We still have this intensely strong gravity, and the neutrons are all crowded against each other trying to hold the thing up.
It's possible that neutron stars that exist in binary systems can collapse into black holes by stealing material from their companions.
And so as I begin piling stuff on it and it begins shrinking further, it will shrink to a point where it becomes a black hole. And actually nothing can halt its collapse then. So all the matter that was in the core of the star just disappears down the black hole, ends up at the center of it in some form, and the star essentially winks out.
Supermassive stars can collapse into black holes under their own mass and do not need to steal mass from a companion. Nor do they necessarily create the tremendous supernova explosions which accompany the births of neutron stars.
About 1 or 2 dozen well-substantiated black holes now exist of the stellar variety, okay? And they typically have masses of around 7 or 10 times the mass of the sun. Many of them seem to have a mass of 7 times the mass of the sun. So there's something about stars, massive stars at the ends of their lives, which seems to drive them toward a preferred mass range of 7 solar masses or 5 to 10 or 12, something like that. Even stars that started out with, say, 50 times the mass of the sun or 60 appear to generally lose most of their mass during their lives before collapsing to form the black hole. And they collapse when their mass is only 7 or 10 solar masses, not 50 or 60. So that's telling us something about mass loss during the normal lives of stars. In those cases where the star's core collapses to form a black hole directly, instead of first forming a neutron star as an intermediate stage, there are not many neutrinos emitted. And so in that case, not only does the core of the star collapse to form a black hole, but the surrounding layers of gas also collapse and contribute to the mass of the black hole. In that case, you don't have a successful explosion. You don't have this expanding remnant of chemically enriched gases. All the gases get eaten by the collapse of the object to form the black hole.
Astronomers may never observe the light of a massive star collapsing directly into a black hole, but there may be other clues to their creation. After Oppenheimer's work in 1939 on neutron stars and black holes, he led the team that developed the first atomic bomb. The creation of that weapon and those that followed would overshadow his work in astrophysics. But it was the United States and the Soviet Union's efforts to control the bomb that resulted in the discovery of one of astronomy's biggest puzzles.
In the 1960s, the United States and the Soviet Union signed a test ban treaty. They agreed not to test nuclear weapons. So the United States put up a series of satellites to monitor the Earth for nuclear weapons. And the way to do that is to watch for gamma ray bursts, because an exploding hydrogen bomb or atomic bomb produces a burst of gamma rays. The scientists were startled when they detected lots of bursts, but the bursts weren't coming from the Earth, they were coming from space. There were lots of gamma ray bursts occurring in the sky.
Astronomers use the term gamma ray bursters to identify the objects that produce these sudden blasts of radiation, and they are still a source of puzzlement. Detailed observations indicate that they are extremely far away and generate the energy equivalent to 1 billion times the energy produced by the sun. But new methods of observation have provided astronomers with more clues, and the mystery may soon have a solution.
In the late 1990s and in the beginning of the new millennium, we've made incredible progress in understanding at least certain types of gamma ray bursts. They appear to be associated with the collapse of massive stars. And in fact, we have seen successful supernovae associated with some of these gamma ray bursts. There's a gamma ray burst, and then in the few weeks thereafter, you see the supernova light rising and then declining. So apparently some supernovae, during the process of core collapse, are able to channel a tremendous amount of their energy into these very high energy gamma rays.
These supernovae associated with gamma ray bursts are called hypernovae, produced when an extremely massive star collapses into a black hole.
So somehow the formation of a black hole is accompanied by a jet of material squirting out at very, very high speeds, close to the speed of light, but not quite at the speed of light, which, if it's pointed toward us, forms a gamma ray burst.
Most scientists now agree that gamma ray bursts are the birth cries of newly born black holes. But like black holes themselves, gamma ray bursts contain many puzzles. What happens at the moment the black hole forms? What focuses the jets? It was questions like these that drove scientists to push their knowledge even further in the first place, leading them to theorize about these strange end states of stars, these neutron stars and black holes. And now, ongoing research and observations by teams of scientists around the world are helping to answer these questions. An amazing and ironic accomplishment, considering this can all be traced back to a physicist trying to solve the mysteries of the universe and the conflicts of nations on a blackboard.